Hello students, this is the Digital Knowledge Irshad Academy with a new video of a non-inverting feedback amplifier. Before going to circuit description, subscribe my channel, press bell icon for the next video. Also the video is a bit large and it is broken into 3 segments. The first one is non-inverting feedback amplifier, and we know that it has a very large gain. That is the advantage of operational amplifier, but at the same time it has a lot of variations in gain. We have the advantage at one hand, but associated with a variations in gain. Now variations in gain is due to 2 factors. The first one is a temperature, and at room temperature that is positive 20 degrees Celsius, the gain is at 3600, and at minus 40 degrees Celsius the gain increases to 4000, and at 120 degrees Celsius the gain decreases to 2600. Now, although the gain is very large, but there is a lot of variations in gain due to, first is the temperature. At room temperature positive 20 degrees Celsius the gain is 3600. At minus 40 degrees Celsius the gain increases to 4000, and at plus 120 degrees Celsius the gain reduces to 2600. Now this is a variations in gain because of temperature. The second one is a production yield. What is production yield means? The operational amplifiers are made in mass production. There is a mass production. Mass production means they are not made in 10, 20, 50, 60 or 100. They are in tens of thousands. They are made in tens of thousands. And then we cannot rigid to specification. Mean if we want to design or produce an amplifier with a gain of 1500, it is unlikely, it is difficult that all 10,000 should have the same gain. Now the gain varies from operational amplifier to operational amplifier, and the setback is that if we are using an op amp type M 702A, and if it goes defective in a circuit, or it goes unserviceable, then we are not going to use the same type. Why? Because if we buy from the market M702, that might have a different gain which is different from the previous one we are using. Therefore, we'll find out an operational amplifier of same gain, which must have a same gain and not the same type. We must not look for an amplifier which is same type. We must look for an amplifier which has the same gain. Now, if these two problems can be overcome, we can use the operational amplifier satisfactorily. Now, temperature must be stabilized. The gain variations should be minimized. That can be done by using a negative feedback that will stabilize the gain. And see here, this is the circuit, non-inverting feedback amplifier. This is a signal voltage. This is the ZI input impedance. Output control generator AV input 1. Now, this is a feedback factor. The output is taken between this point and ground, and there is a voltage when the current flows from ground through R1 through R2 to ground, and it completes the circuit, and it drops a voltage across R2, and that voltage is called as feedback voltage, and it is called V input 2 is equal to Vf. There is another current flowing which is I with the pink color, and this being so small. Why? Because the ZI input impedance is very high. The input current I can be neglected. There is only one current I1 flowing, and it drops a voltage across to R2 that will be utilized as a feedback voltage. Now, if we have output voltage formula is V naught is equal to A times V input, or simply V naught is equal to A V input. Say for example, the output voltage increases because of gain increases, gain rises, gain is going to be high, and we know when gain is high, the output voltage is going to increase. When the output voltage increases, there is a more voltage drop across R2 that subtracts from Vs. V naught is equal to a Vs minus Vf. When Vf increases, it subtracts from this voltage, and the input across Zi decreases, and when the input decreases, the output is going to decrease. Now, when A tends to increase V naught, V input goes down because of feedback. Therefore, the increase in V naught is counterbalanced by decrease in V input 1. And if gain decreases and it decreases V naught, then when voltage here decreases, gain tends to decrease the output voltage. When the output voltage decreases, there is a less voltage dropped across R2 and it subtracts from Vs. When Vf is less and subtracts from Vs, it is going to increase the input voltage. Now when gain tends to decrease the output voltage, V input 1 increases to counterbalance this decrease in output voltage. Coming to the circuit summary, is a non-inverting operational amplifier. Although operational amplifier has a large value of gain, that is the advantage of operational amplifier, there is a lot of variation in gain that becomes a setback due to temperature and production yield. Temperature, as I explained, at room temperature plus 20 degrees Celsius, the op-amp gain is 3600. At minus 40 degrees Celsius, gain varies to 4000. At positive 120 degrees Celsius, gain goes down to 2600. Op-amp cannot be used where temperature fluctuates. However, if the gain variations due to temperature are reduced, op-amp can be used satisfactorily. This is because of the temperature. Production yield is called mass production. As I said, the operational amplifiers, they are not made in 10, 20, 50 or 100. They are made 1,000 and tens of thousands, and we cannot rigid to specification. It is difficult to rigid to specification. It is just impossible that all 1000 operational amplifier should have the same gain. Due to mass production, gain of typical op-amp M702A varies from 2400 to 6000. If an op-amp in a circuit goes unserviceable, it cannot be replaced with the same type of operational amplifier. This point is to be emphasized, that if you are using an op-amp of M702A type and it goes unserviceable, we just cannot go and buy from the market and replace the same type. We must look for an operational amplifier which has the same gain. If an op-amp in a circuit goes unserviceable, it cannot be replaced with the same type of op-amp. Amplifier which has the same gain is to be used in the circuit. Solution: negative feedback is used to stabilize the gain. Now the non-inverting feedback amplifier, V input 1 is a Vs, source voltage or signal voltage. V input 2 is coming across R2, which is feedback voltage, and V input is equal to Vs minus Vf, and V0 is a V input 1 can also be written as a Vs minus Vf. If due to temperature gain A increases, output V0 increases. Here, if due to temperature gain A rises, this arrow shows rising. A increases, it increases. Vf increases. Vf subtracts from Vs, therefore V input decreases, hence V not decreases. Gain A tends to increase V0, but feedback is increased and it subtracts from the signal voltage, and V input decreases, and hence VO comes to its original value. And when gain A tends to decrease, now gain A is decreasing due to temperature, it is going to decrease V0. Vf across R2 increases, V input increases, that increases V naught. Once again, if due to temperature the output voltage increases, there is a more voltage drop across R2, and this voltage subtracts from signal voltage. Therefore, V input decreases. When V input decreases, the output decreases. The moment V out increases due to variation in temperature and gain A tends to decrease the output voltage. The voltage across R2 decreases. It subtracts from V signal voltage, and the V input increases, that will increase V naught. The amount by which the V naught was falling, it is counterbalanced by decreased in feedback. Here, when gain A tends to increase V naught, the feedback voltage increases, which subtracts from this, and V input decreases by the same amount, and the V naught remains constant. In the second case, if the gain A tends to decrease the V naught, the Vf voltage, feedback voltage, will decrease, and it subtracts from signal voltage, and V input increases by the same amount, and the V naught becomes constant. Going over to main points again. Non-inverting feedback amplifier. V input 1 is a source voltage. V input 2 is a Vf voltage, feedback voltage across R2. And V input finally applied to input impedance is equal to Vs minus Vf. The output control generator output formula is V naught is equal to a V input. V naught can also be written as V naught is equal to a Vs signal voltage as source voltage minus feedback voltage. If due to temperature gain A increases, output V naught increases. Here, when gain A increases, V naught increases. Feedback Vf increases. Feedback Vf will increase across R2, and it subtracts from Vs. Therefore, V input decreases, hence V naught decreases. The amount by which V naught was increasing is brought back to original value by feedback voltage. When gain A tends to decrease V naught, now V naught is decreasing. The feedback voltage decreases, subtracts from Vs, and the duty of Vf is to increase V input, that will increase V naught. Here, when gain A decreases the output voltage, feedback voltage decreases, which will increase V input, and the decrease in output voltage is counterbalanced by the V input voltage, and virtually by feedback voltage is responsible for keeping the output voltage constant. In the next video, we will study the derivations of formulas. Thank you very much.